It is a pleasure to be in this International Congress on Category Theory. My name is Carlos Segovia from UNAM-Oaxaca in Mexico. I'm going to talk about the classifying space of the G-cobordism category, all the results you can find in this article on the archives. The cobordism category without the G has as object finished disjoint union of circles. The morphisms are two-dimensional cobordism, and here we have three examples. The first one goes from 3 circles to 3 circles and has genus 2. The second is a cobordism that goes from the one-dimensional empty manifold to one circle. The third is go from 3 circles to 1 circle. The first person that studied the classifying space of this category was Ulrika Tillmann, and she proved that the connected components are trivial, the fundamental group is the integers, and the classifying space splits as the product of the circle and an infinite loop space that is simply connected, and that I put it with X. Later, together with Galation, Madsen, and Weiss, they show that the classifying space is the initial space of a certain tone spectrum. And I want to remark that these two categories are in essence different because the first one is discrete and the second is a topological category. The technique used by Galation, Madsen, and al. was a generalization of the Thom theorem that says that the Bordism group can be presented as a homotopy group of some space. The process used by Tillmann worked with subcategories. Here, S0 is the subcategory of closed surfaces. S bigger than 0 is the subcategory when you don't allow the empty manifold. S1 is a category with only one object given by the circle and connected surfaces. So all the morphisms are given by the genus. As you can see, the S0 is just the infinity product of the natural numbers, and S1 are the integers. S1 can be included in this big category, but we can find an adjoint functor constructed as follows. You choose a cobordism from N to M, and then you assign G plus M, where G is the genus plus the exits minus the connected components. My apportation is that this can be seen in a geometric way just by gluing by the right a pair of pants with multiple legs. For example, here for a cobordism from 4 to 4, you assign the value 2 because if you glue by the right, you count the genus and this is 2. This also gives you the natural transformation of one of the two compositions because E composed by phi is the identity, but the other no, and you can find a natural transformation. So these two spaces has the same classifying space, and S0 has a classifying space, the infinity torus. Also, we have that the inclusion of S1 in the whole category and the extension of phi with negative values, this is give the inclusion of the natural number into the integers, and this is a multiple equivalence in classifying spaces, and this implies the splitting where X is the homotopy fiber of this functor. When we work in a G-covariant version, we take the objects now are principal G bundles over disjoint union of circles, and the morphisms are cover these classes of principal G bundles over surfaces. For objects, I put here two examples, one for the cyclic group of order 4, and we can show that every principal G bundle over the circle is given by one element of the group that I call the monodromy. For example, here you can, for X, we have a principal G bundle given by a circle mapped by a degree 4 map to the circle. For the morphisms, all of them are the gluing of elementary part given by principal G bundle over the cylinder, the pair of pants, and the disk. For the cylinder, there are conjugation. For the pair of pants, there are products. And for the disk, since it's contractile, there is only one that is trivial. So the monodromy is trivial. Also, for the pair of pants with multiple legs, you can see as here, and An important issue for the handle body, the exit has monodromy, an element of the commutator group. And these two show that the connected components are the abelianization of the group. An important assumption for the category is that for every connected component, they are the prefactorization of a G-cobordism over a pair of pants with multiple legs. The reason is because if you see here the classifying space of the whole category, you will see a lot of spaces glued to them that in a joint, and they are the classifying space of some isotopy automorphism groups given by some conjugacy classes of some elements, and we have to cut it because if not, the classifying space is a mess. And I call this like verrugas, and I cutting here with a machete that verrugas. I also studied the fundamental group of this classifying space, and for this we have to use the left calculus of fraction and a quotient category given by this equivalent relation that is just the inverse for the connected sum. We choose a subset of morphs given by the closed set G-cobordism plus the identity cylinders. We can show that the groupoidal fraction is just this quotient category when we make the localization in this subset of morphisms. We can show some relation called the chimera relation, that is just you glue some cobordism in this way and just you glue in another way, yeah, that we have here sigma 1, sigma 3, sigma 2, sigma 4, and see that we change sigma 1, sigma 4, sigma 2, and sigma 3. So, and the important thing is that this happened for the work of Galatian, Madsen, Tillmann, and Weiss. We proved also a splitting short exact second between the fundamental group and the integers and the two-dimensional homology group. And for that, this showed that the fundamental group is this sum. The generalization of the Tillmann setting use also the same subcategories, but in the Jacobian version, and we show the isomorphism between the closed G-cobordism subcategory with the infinity product of the natural numbers. We have also the adjoint functor between this inclusion, and this is constructed in a geometric way just by gluing by the right by a G-cobordism over a pair of pants, and this we have also the natural transformation between one of the two compositions, and this shows that these classifying spaces has the same homotopy type, and well, that the classifying space here is also an infinity torus, and we also have this inclusion, but this shows that the classifying space is the abelianization product and space that is a homotopy fiber and the circle. But now the fundamental group of this space is the two-dimensional group of G. As conclusion, then we show that the connected components are just the abelianization of the group, that this is the first Bordis group for G. We show that the fundamental group is this the sum of the integers plus the two-dimensional group of G, and that the classifying space is just the abelianization, the circle, and the space that has the fundamental group, the two-dimensional homology. And we can see, we compare here with the work of Galatian, Madsen, Tillmann, and Weiss in the G-cobordism case, and we have the same for the connected components and the fundamental group. The other is just the initial space of a certain tone spectrum. And these are the papers you can check in the archives, the work of Tillmann and also the paper of Galatian, Tillmann, Madsen, and Weiss. And here for the fundamental group. And whenever this thing of the pandemic is over, everyone can be is invited to come to Oaxaca. Oaxaca is a really nice place, and well, thank you for